A magnet invention first conceived at the University of Minnesota is making headlines tonight after being ranked one of the best of the year by Time magazine.
A hidden force powers your world. Not oil, not solar, not even the grid. Magnets.
From everyday electronics to industrial machines.
Magnet is everywhere, yeah.
They're everywhere, woven into every screen, motor, and machine. Without them, the modern world would come to a halt. But now, a discovery has changed everything.
This clean earth magnet could eliminate the need for mining rare materials.
A company claims it's built super magnets, far stronger than anything we've known.
A new type of magnetic material called iron nitride. This material is going to change the world.
They could revive machines once dismissed as science fiction, machines once thought absurd, ignored by science and starved of funding.
Iron nitride happens to have the highest magnetic field strength of any magnetic material.
In this episode, we'll take you through the story of supermagnets and the quiet battle to reinvent the laws of energy, the magnet force behind clean energy. Most of us rarely stop to think about what powers the machines we use every day. But inside the devices that sweep our floors or take us to work, there's something small and quietly essential, doing the heavy lifting. Peek inside the motor of your vacuum cleaner or your electric car, and you'll find a shared secret. Despite their differences, both rely on a single key component, the permanent magnet. It's a tiny force with an outsized role in making modern motors run. The magnets stuck to your fridge, pinning up birthday cards and to-do lists, are the basic kind, ferrite magnets. They're cheap, common, and fine for simple tasks. But when it comes to serious performance, they don't come close. For high-tech devices, a whole different class of magnet is needed. These are far stronger, made from rare earth metals, a group of elements that quietly shape the modern world. These metals can generate a magnetic field on their own without any electricity. That makes them incredibly valuable in motor design, where converting energy efficiently is everything. Metals like neodymium and dysprosium are the stars of the show. They don't just make motors run, they make them smaller, lighter, and more efficient. They power the buzz in your headphones, the smooth spin of your phone's vibration motor, and the detailed images from an MRI scanner. In wind turbines, they sit deep inside generators, helping turn a breeze into clean electricity. In electric vehicles, they move wheels with less drain on the battery. As we charge into an era of renewable energy and electric transportation, the world's hunger for rare earth materials is only growing. Electric cars are rolling out in record numbers. Wind farms stretch across coastlines and farmland. Every new motor, every turbine, adds to the demand for these powerful elements. But now comes the real test. Can the world's supply chains keep up? The mines that dig up these rare earths and the factories that refine them are already under pressure. Bottlenecks are forming. Delays are growing. If production can't scale fast enough, the ripple effect could slow down everything, from how we get around to how we power our homes. A rare earth-free future. What if the future of energy didn't depend on faraway mines, fragile trade routes, or materials pulled from the edges of the earth, but something simpler, smarter, and closer to home? Rare earth elements might sound exotic and scarce, but that's only half the story. They're actually found all over the planet, in soil, rock, even in everyday materials. The real challenge isn't finding them, it's extracting them. These elements don't form in neat, concentrated veins. Instead, they're scattered like glitter in a sandbox, tiny particles hidden inside much larger chunks of material. To pull out just one rare earth metal, say neodymium, tons of rock must be crushed, chemically treated, and painstakingly refined. It starts with mining massive quantities of ore. That ore then gets cracked open and bathed in chemical solvents that tease out the metals we need. After that, the purified elements are baked and fused into powerful magnets. But this isn't a clean process. It demands huge amounts of energy, complex infrastructure, and often leaves behind a trail of toxic waste, especially in water systems, where chemical runoff can linger for years. And that's not the only problem. Right now, nearly 90% of the world's permanent magnets come from a single country, China. That's not speculation. It's straight from the U.S. Department of Commerce. This tight grip on global supply makes the entire system dangerously vulnerable. Over a decade ago, a diplomatic dispute between China and Japan caused rare earth shipments to grind to a halt. The ripple effects hit industries around the world, exposing just how fragile and how centralized our magnet supply chain really is. But now, something might be changing. In a quiet corner of Minnesota, a startup called Newmans Magnetics is working on a solution that could rewrite the story. Their new innovation? The Clean Earth Magnet. It's designed to deliver the same high performance needed for electric motors, wind turbines, and smartphones, but without using any rare earth elements at all. No toxic mining, no global supply drama, no extra cost. It's not just a cleaner magnet, it's a clean break from the way things have always been done. And if it lives up to its promise, it could mark the beginning of a more sustainable, more resilient future. One where the building blocks of modern technology come not from scarcity, but from ingenuity. Clean Earth Magnet. The science behind the Clean Earth Magnet isn't exactly new, but unlocking its full potential has felt like chasing a ghost. Researchers have long known about a rare form of iron nitride, the alpha double prime iron nitride, with magnetic strength that could go toe-to-toe with traditional rare earth materials. But there was one big problem. Every time they tried to create, it changed, like a shapeshifter. The material would lose its supermagnetic edge and morph into a more ordinary, weaker version of iron nitride. But then, the tide turned. A team at Newmans Magnetics figured out how to stabilize this elusive material, but at a scale so small it was almost invisible. Using cutting-edge techniques like chemical vapor deposition and liquid phase epitaxy, they managed to grow tiny particles of the powerful alpha double prime phase. Then, they compressed and sintered those tiny particles into solid, functional magnets, ones that could be shaped to fit modern machines. No rare earth metals, no environmental fallout, just raw, reliable power. This isn't just a cool science trick, it's a potential revolution. If this tech scales, we could ditch rare earth mining altogether. Imagine electric vehicles, clean energy systems, and next-gen machines running on magnets built from something smarter, cheaper, and way more sustainable. Iron nitride's edge. Magnets at their core owe their strength to electrons. These are tiny, charged bits found in every atom. When enough of them spin in the same direction, they create a magnetic field. But not all elements are created equal. Some have more free electrons than others, and it is those free, spinning electrons that make a difference. The stronger the alignment, the stronger the magnetic pull. Iron has no shortage of free electrons. But on its own, those electrons tend to point in opposite directions. Their energies cancel each other out, weakening the magnetism. That is why iron by itself is not always enough. When elements like neodymium or dysprosium are added, they help bring order to the chaos. These rare earth metals shift the structure of the iron, giving its electrons a way to spin in the same direction, which turns the material into a strong, reliable magnet. What makes iron nitride so unique is that it manages to organize those electrons without needing any rare earth metals. It creates a tight structure where iron atoms hold together in a way that keeps the electrons spinning together. This alignment is what makes it so effective. In electric motors, the strength of a magnet is measured using a unit called the Tesla. If you are more familiar with Earth's magnetic pull, 1 Tesla equals about 10,000 Gauss. To give a sense of comparison, common hard ferrite magnets, which are made from iron oxide, usually reach no more than 0.35 Tesla. That is enough for simple devices, but not for things like electric vehicles or wind turbines. The most powerful neodymium magnets used in today's motors tend to reach between 1.4 and 1.6 Teslas. Newmans Clean Earth magnets, built using iron nitride, have shown results that go even higher. They reach a magnetic strength of 2.4 Teslas. That is a significant jump. Not only are they stronger, but tests have shown that they also hold their magnetism better across a wide range of temperatures. This makes them more dependable for machines that operate under tough conditions. A material that strengthens magnetism without needing rare earth metals could be more than a breakthrough. It might open the door to cleaner, more efficient machines that are easier to produce and less tied to complex supply chains. Less waste, more power. A breakthrough on its own can make headlines, but a breakthrough that's clean, scalable, and affordable, that's the kind that rewrites the future. That's where Neyron's clean earth magnets step into the spotlight. Unlike traditional magnets that require rare materials from distant mines and delicate supply chains, these can be built start to finish under a single roof. No exotic equipment, no globe-spanning logistics, just one streamlined facility. And the impact? Massive. The process slashes carbon emissions by over 80%. Water use? A fraction of what conventional methods require. And despite all that efficiency, the final cost remains comparable to rare earth magnets, minus the unpredictable price hikes driven by politics or shipping bottlenecks. But it's not just about what they leave out, it's about what they use. The iron comes from iron salts, byproducts of steel production that were once tossed aside as waste. Now they're part of something far more valuable. The nitrogen? It's drawn from ammonia. But if that ammonia is made using clean energy, air, and water in regions that produce extra solar or wind power, then it doesn't just deliver clean nitrogen. It also creates hydrogen. And that hydrogen can go right back into powering the process, forming a loop that's elegant, efficient, and far less polluting. Now let your mind wander for a bit. Imagine what could happen if these clean earth magnets were paired with experimental free energy devices. Machines from decades past that showed promise but were shelved due to material limits. What kind of performance could we see now with stronger, sustainable magnets at their core? The possibilities could be far more extraordinary than anyone imagined. And if this glimpse into the future has sparked your curiosity, now's the perfect time to hit that like button and stay tuned. Because this story, it's only just beginning. The magnet rotor. There are ideas that catch fire long before the world is ready to understand them. That was the case with Howard Johnson. He was not a typical inventor. Johnson believed magnetic force alone, without any external power, could drive machines, and he dedicated his life to proving it. His work centered around permanent magnet motors. What made his ideas so unusual was the claim that they could work without input from batteries or fuel. That claim raised eyebrows, but it also opened the door to a kind of thinking that looked far past fossil fuels and expensive energy grids. His first key invention was the magnetic rotor. It used a set of permanent magnets placed carefully around a central shaft. When the shaft turned, the magnets interacted in a way that produced a magnetic field strong enough to generate current. This current could then be used to power electrical equipment. As the rotor kept spinning, the movement of the magnets sustained a flow of energy that did not depend on anything but their arrangement. He didn't stop there. Johnson later developed a more advanced version, a permanent magnet motor that could maintain its own operation. This motor was designed to generate electricity without needing any outside source of energy to get it going or keep it running. His idea was so bold that many people dismissed it. Still, Johnson secured a U.S. patent for it in 1979. Legal challenges followed, but after years of pushing forward, the patent stood. Even more surprising were the results of independent testing. Some researchers who reviewed Johnson's designs found that the motor could indeed produce electrical power on its own. Reports suggested that under certain conditions, the device was capable of producing up to 20 kilowatts of continuous electricity. That level of output could run multiple household appliances at once, or even support a small home or workshop. Now imagine what could happen if you took Johnson's designs and combined them with the clean earth magnets developed by Neyron Magnetics. His original system depended on the magnetic force created by older types of permanent magnets, which had clear limitations. They were weaker, less reliable, and prone to losing strength over time. But Neyron's magnets can produce up to 2.4 Teslas of magnetic force, far beyond what was available in Johnson's day, and they hold their strength across a wide temperature range. even more important, they are stable and sustainable. Incorporating these new magnets into Johnson's inventions could change everything. The improved magnetic field strength would increase efficiency and consistency. Systems that once needed large parts or special conditions might be miniaturized, more reliable, and cheaper to build. What was once limited by the materials of its time might finally get the chance to show its full potential. Joseph Newman's energy machine. When Joseph Wesley Newman introduced his machine, few could decide if it was genius or delusion. He was an American inventor with bold ideas. He introduced an energy machine that led to both curiosity and controversy. According to Newman, his machine produced more mechanical power than the electrical energy it consumed. At its core was a direct current motor. But unlike conventional designs, Newman believed his device pulled additional energy from the mass of copper coils based on Einstein's famous equation that links mass and energy. He also suggested that the motor drew from the quantum fluctuations that occur in magnetic fields. The science community met these ideas with mixed responses. Some physicists backed his claims, even providing affidavits to support the machine's operability. Yet for many others, the concept felt impossible. Mainstream physics did not support devices that appeared to violate the fundamental laws of thermodynamics. By those standards, a machine that produces more energy than it receives in input cannot exist. And so, when Newman applied for a United States patent, it was rejected. The reason was simple. The Patent Office could not grant approval to a machine that made claims not grounded in accepted physical principles. Further testing brought more issues to light. While the device did run, its performance did not match Newman's boldest assertions. It failed to operate at full efficiency, and it did not generate more energy than was supplied to it. That only deepened the doubts. For many, the dream of a self-powered energy machine faded into the background. However, technology has not stood still since Newman's time. Now, consider what might happen if his invention were re-evaluated using today's advanced materials. Nylon Magnetics clean earth magnets are capable of generating stronger, more stable magnetic fields than anything available to Newman. These magnets can hold their magnetic strength across a broader range of temperatures and are far more efficient. If they were integrated into Newman's design, the system might operate with less energy loss and greater mechanical advantage. Even if it does not break the rules of thermodynamics, it could push the boundaries of what is possible using current laws of physics. The idea of enhancing performance through better materials may not be the dream of free energy, but it certainly opens the door to more efficient and reliable designs that Newman could only imagine. The SURL effect generator. If magnetic motion alone could generate endless energy, then John Searle may have been decades ahead. First introduced in the 1960s, the SURL effect generator, or SEG, came from the mind of British engineer John Roy Robert Searle. He believed he had found a method to create electricity using only magnetism and motion. The SEG's structure was as complex as it was ambitious. It was made up of 3 stationary stator rings and several rollers that orbited around them, all constructed using specially magnetized materials. As these rollers moved through the magnetic fields of the stators, electric currents were generated. There was no physical contact between the parts, meaning no friction, no heat, and no material wearing away. Searle described it not just as a generator, but as something capable of producing a kind of endless motion. He even claimed the device could defy gravity when it reached certain high-voltage levels. According to him, the SEG had shown signs of levitation under specific conditions. That alone pulled attention from curious minds, though it also led many to label the entire thing as impossible. He took it even further by engraving sine waves onto the device's components, convinced that it would improve how it functioned. The interaction between moving magnets and copper was thought to act like a combination of a magnetic capacitor and an electric capacitor. As the system moved, this dual capacitor effect was expected to create a consistent flow of electricity. As magnets spun across copper surfaces, the electric capacitors could be charged and discharged repeatedly, delivering usable power without drawing from any external energy source. However, critics did not hold back. Some dismissed the SEG outright, calling its concepts outlandish and accusing SURL of twisting physics into fiction. They argued that it broke the rules of how energy behaves and saw no need to explore it further. For them, the SEG was nothing more than another failed attempt at a perpetual motion machine. But one has to wonder, what if the SEG had been given access to materials that didn't exist in SURL's time? Now imagine the difference if Neyron Magnetics clean earth magnets were used to build an updated version of the SEG. These magnets are not only free of rare earth materials, but they also offer high performance with lower environmental impact. Since they can be manufactured with iron and nitrogen sourced from industrial byproducts and clean processes, they represent a leap forward in both sustainability and practicality. When paired with the SEG's contactless design, the stronger, more stable magnetic fields produced by Neyron's technology could drastically increase output and reliability. The rollers might move more efficiently, the magnetic interactions could be more precise, and the entire setup might come closer to achieving what SURL had once hoped for: sustained motion generating real power. If the concepts behind the SEG were revisited with these new materials and modern engineering, it is not far-fetched to think that the results could surprise even the harshest skeptic. The Bedini pulse motor. John Bedini, an inventor and electrical engineer, spent much of his time exploring ways to change how we think about energy. He focused on devices that operated differently from traditional systems, venturing into areas that most engineers often dismissed. One of his better-known innovations was the Bedini pulse motor, a machine built to run using timed electromagnetic pulses rather than continuous current. The basic design used a spinning rotor lined with magnets, positioned near a stator wrapped in coils. When activated, magnetic forces would interact with the rotor, pulling it forward and triggering a pulsed rotation. What made the system stand out was not just its motion, but what happened during that motion. As the rotor turned, it had the ability to produce electric current within the coils it passed. That meant it could take mechanical energy and turn it back into electrical energy, often in real time. Many of Bedini's experiments focused on using that regenerated power to charge lead-acid batteries. He believed that rather than wasting energy through heat or resistance, his system could capture and recycle what would otherwise be lost. The motor itself could be built in several configurations. Some setups used a single phase, while others relied on more complex multi-phase arrangements. Each version had its own advantages depending on the goal. To control the flow of energy through the system, many designs included electronic circuits that handled the timing and length of the pulses. This precision helped the motor run more efficiently and could push its performance closer to what Bedini had envisioned. There were also ongoing debates about what the pulse motor could truly do. Supporters claimed it had the potential to produce more energy than it consumed, which placed it into the controversial category of over-unity devices. They believed that by managing the energy output and reclaiming what was typically lost in conventional machines, the Bedini motor could offer a different path to long-lasting energy solutions. However, the scientific community was largely skeptical. Critics argued that no matter the setup, a device could not consistently create more energy than it used without violating fundamental physical laws. Still, the foundation that Bedini built raised interesting questions, especially when viewed through the lens of modern materials. If the Bedini pulse motor were rebuilt using clean earth magnets developed by Neyron Magnetics, it could lead to entirely new results. These magnets are designed without relying on rare earth elements, using a combination of iron and nitrogen that maintains strong magnetic properties with better sustainability. With stronger magnetic fields and reduced losses from heat and friction, the motor could operate more smoothly. The strength of the clean earth magnets could allow for more efficient pulse intervals, improving how energy is both used and recycled within the system. This kind of upgrade might not only enhance performance, but also help resolve some of the challenges critics pointed out years ago. There is no guarantee, of course, but pairing Bedini's concepts with new materials like these could take what was once dismissed and bring it closer to actual use. Free energy or false hope? Somewhere between belief and science sits a strange space filled with unfinished ideas. It is where concepts like free energy machines continue to exist, not because they have been proven, but because they have never truly disappeared. Every few years, an invention is revisited, a new material is discovered, or a fresh approach begins to take shape. The idea does not go away, it waits. What adds to the interest now is the growing demand for alternative power. As the need for cleaner energy rises, so does the pressure to rethink methods once pushed aside. Devices once thought useless are being viewed again through a sharper lens. The technology used to build them has improved. There is still resistance, of course. Many say the idea of getting more energy out than is put in cannot be made real, but not everyone agrees. Quiet work continues in labs and garages across the world. Some chase efficiency, others chase proof. No matter the reason, progress is being made, piece by piece. The larger point is not whether these machines work today. It is what they represent about the way we approach energy, limits, and change. Inventions are rarely perfect the first time. Sometimes they need to wait for the right moment or the right material. And when that moment comes, everything can shift in a direction no one expected. If you found this topic as fascinating as we did, don't just leave it here. Give that subscribe button a gentle push and stick around for more. Thank you for watching. See you in the next video.